And we're just going to do, we are live. Fantastic. Usman, can you just check? Chris, if you can just do a mic check so we can make sure that people who are watching it live can hear you.
You mean Scott?
Yeah, Scott, sorry, yeah.
Check, 1, 2.
Check, 1, 2. Yeah, we can hear you. Live's working perfectly fine.
Thanks.
Ready to go.
Okay, we're ready to go.
Okay, we're ready to go.
Okay. Then welcome everyone to the demo of the Metavisionaries course. This course is called Introduction to the International Space Station. And we're going to talk about this great engineering and international partnership accomplishment that orbits the Earth. And so, does anyone in the audience know what's in the picture here? Anyone can just speak freely if they know what's in the picture.
Cupola.
Yeah, exactly. This is a window in the International Space Station that faces Earth. And it's used for observation of the Earth, photography, and it's a really, really nice place. So what we'll do today is give a brief introduction to the space station. And I'll go to the next slide here. Oh, this is about me. Who am I? I'm Scott Ritter. I'm a researcher at the German Aerospace Center, and I do experiments on the International Space Station. And I'm also a graduate of the International Space University, which focuses on all things space. So I'm very delighted to be here and talk to you about the International Space Station. So this course is meant to be 5 days long, but today, being the demo day, we're only going to talk about the first course, which is talking about the history, the development, and the evolution of the space station. In future weeks, this will be 5 days, and the second class will be on the scientific research that's done aboard the space station. The third class will be about the operations of the International Space Station. The fourth class will be on human activities, and the fifth class will be about the future of the space station. So if you'd like to learn more about the space station beyond what's in this demo day, then go ahead and sign up on the Metavisionaries website and look for the International Space Station course. And you can sign up for the additional courses. So we'll only talk today about the first course, the history and development and evolution of the space station. And before we get into that, does anyone know what's in the picture right here?
Yeah, so that's the ISS, if that's what the slide we're looking at.
Yeah, exactly. That's the ISS. And this is a project that was developed over the course of over 10 years. This was built over 10 years. And what you see here is the ISS in its completed configuration. This photo was taken in 2011 after the configuration was complete. And what you see here is also what's beneath us in the floor. If you look in the floor, you'll see the same thing. And on the left and right are the big solar panels that power the space station. And they're attached to the space station in the middle by a big truss. And then you see the silver cylinders on the bottom and the white cylinders on the top, those are the modules where the people work and live. And so we'll talk about how all of that was built and what all of those modules are. So here we go to the next slide. So this summarizes today's course. We'll talk about three things: the history of the space station, how it came to be, the previous space stations, why it exists, and how it was developed. That's number one. Number two, we'll talk about the development of the space station, how it was assembled. We'll look at some 3D models of it, including the one that's under the floor, and the launch vehicles that were used to build it, which include the ones that are flying around us here. We've got one over there, and there's a Proton rocket somewhere. But there's a lot of years and a lot of work that went into building it. And then we'll talk finally, number three, about the evolution of the space station, what it will become in the future. And in the end, we hope that you'll be able to answer some frequently asked questions about it. But before we begin,
here.
Yeah. Okay, there it is. Cool. But before we begin, I'm just going to speak briefly about the partnerships. This great achievement, this International Space Station, wouldn't be possible if not for the partnerships of these 5 space agencies here. Does anyone know what the space agency on the left is? Can anyone read Russian?
Roscosmos.
Yeah, Roscosmos. Yes, Roscosmos is a major partner. The second space agency is ESA, the European Space Agency. The third space agency is JAXA, the Japanese Space Agency. The fourth is CSA, the Canadian Space Agency. And the last is NASA, the US Space Agency. And all of these partners combined efforts to operate the International Space Station. And on the right is the symbol of the space station. It's a picture with 5 little stars to represent the 5 partners and all the flags of the countries that contributed to its early development. And the list of flags is growing and growing and growing, even still. So that's a summary of what we'll talk about today. Let's get into it. So the history of space stations. This International Space Station was not the first space station. It's the biggest space station, but it's not the first. The first space station was called Skylab, and that was made by the US, and it was in operation orbiting the Earth from 1973 to 1974. So a pretty short time. And a picture of it is on the left in the slide, but if you want a real 3D model of it, it's above the seats in the lecture hall there. And Camila's moving it around. That's Skylab. And that was a hollowed out Saturn V segment that was converted into a laboratory for a lot of early human spaceflight research. And on the back of it is the Apollo capsule that brought crew members to the space station and transported them back home. So that, again, orbited the Earth from 1973 to 1974, but it was decommissioned and made way for future space stations. The next space station on this slide is called Mir, and it was in operation from 1986 to 1997 and then decommissioned in 2001. And it wasn't the next space station after Skylab. There were several space stations between Skylab and Mir, but this space station Mir was the crown jewel of Russian space stations. And you can see it's got several modules. It's a complex facility with numerous solar panels, and it was the largest and most capable space station of its time. And then finally on the right, we have the current space station, the International Space Station, which came immediately after the Mir space station. And this space station began in 1998 and continues operation today. And I put it here as a comparison to the other two because I want to emphasize just how big it is. It's very, very big. It's over 4 times larger than the Mir space station and over 5 times larger than the Skylab space station. So the capabilities are much greater, and this was only possible thanks to the partnerships between the 5 space agencies that I spoke about in the previous slide. So this great achievement orbits our Earth today, and we're going to talk about its early construction in the next slide. So the historical rationale for this space station actually began in the 1980s because the United States conceived of its own space station as the predecessor to the Skylab space station with collaboration with Europe and Japan. And in parallel, but independently, Russia was conceiving of its second space station, its follow-up space station to the Mir. And that space station was called Mir 2. But in the 1990s, Russia and the US decided to combine their efforts. And so the Freedom space station, shown in the big picture, and the Mir 2 space stations, shown in the small picture, were effectively combined to become the International Space Station. And through this partnership, it became the preeminent research facility in space to do medicine, technology, and science research. And so that leads to the question, what actually is the International Space Station? If anyone could sum it up in one word, it's a laboratory for doing research. That's the purpose, that's the function of the space station. It's a laboratory. And to be more accurate, it's a group of several laboratories, laboratories from each of the partners of the International Space Station. So for example, Japan has a laboratory, Europe has a laboratory, the US has a laboratory, and Russia has several laboratories. So these laboratories are all connected together and orbit the Earth and allow the opportunity to do science that could not be done on Earth, that takes advantage of the weightlessness in space. So I'm going to go to the next slide and talk about the assembly of the space station, how it developed. So in 1998, this space station was, the assembly of the space station was begun, and it was launched to space using 2 workhorses. The big workhorse on the left here is called the Proton, and it's the rocket that launched the majority of the Russian components of the space station. It has been in operation for many, many decades, and it's a very, very reliable system for getting objects into low Earth orbit. And what you see here on the slide in the upper left corner is a picture of the initial modules of the space station. So these 2 modules were mated in 1998. The white module on the top is called Zarya. It's the very first piece of the space station launched on a Proton rocket by Russia. And the second piece is the gray piece. It's called the Unity Node 1, and it was launched by the US 1 month later in 1998. And the system that launched these pieces, this piece from the US is shown on my right. It's the space shuttle, and it's a similar system to the Proton in that it carried large objects to low Earth orbit. But as you can see, it's the concept and the design is totally different. The Proton was made to be a one-time use rocket, and the space shuttle was made to be reusable. At least the black and white airplane looking part was made to be reusable. So this,
I think we have a question by Isha. She was raising her hand.
Oh, is that right? Go ahead, please.
Isha, you can unmute yourself.
Oh, hi. Sorry,
Hi,
I didn't
Isha.
have a question. I was waving hi to everybody. But please continue. I'll ask my question at the end.
Ah, okay. Hi, Isha. I'm waving too. Okay, so the point of this slide is to show that there were two big workhorses, the space shuttle and the Proton rocket, that built the space station. And the first two modules began in 1998, and they're shown in the top left of the slide. In 2011, all the pieces were assembled in the final configuration. And since 2011, science has been the focus on the space station by using the laboratories that are now there. So I'll go to the next slide, and you can see pictures of the real space shuttle docking and helping to assemble the space station. And on the right, you can see the assembly of additional modules on the Russian segment, the additional modules attached to the original Zvezda module. Does anyone know what Zvezda means in Russian? Zvezda was the first module on the space station. Does anyone speak Russian?
I can read it a little bit, but I stopped my classes.
Zvezda means dawn. So like sunrise, basically. And that's a great name because it was the first piece of the space station. And it's still working today. So I'll go to the next slide. And here is a slide showing again the launch vehicles that were used in the construction of the space station. So on the left, we have the Proton rocket, the big white one in the lecture hall. And in the middle, we have the space shuttle, the black and white one that was reusable from up until 2011. And in the middle here, we have the Soyuz, which brought some pieces also to the space station. And these great machines built this orbiting laboratory that we have today. The next slide shows the vehicles that bring cargo to the space station, because we've got people there and we've got science experiments. These machines brought those assets to the space station. So the Soyuz that's floating around right there, that brought little capsules with experiments, cargo, food for the astronauts. And this little vehicle is called Progress. Those Progress vehicles docked to the Russian side of the space station. In the middle we have this space shuttle that can dock to the US side of the space station. But the space shuttle was decommissioned in 2011 and made for a new system called SpaceX Cargo, Cargo Dragon. And that SpaceX Cargo Dragon is a commercial company that is, there is floating around. And that one is fully reusable. So it took the concept of the space shuttle and rather than only reusing a part of it, the black and white part, it reuses a lot more of it. And that enables cost savings and allows the space agencies to spend money on different things. So those three vehicles brought cargo to the space station. What about the people? So these three machines on the slide brought the people to the space station. Number one is the Soyuz capsule, which brings people to the Russian segment. The space shuttle brought people to the space station up until 2011 when it was decommissioned. And nowadays, SpaceX Crew Dragon brings people to the US side of the space station. And these great systems were incredible for bringing people over many, many years to the space station. And if you want to see a real SpaceX or space shuttle, you can see them in several cities in the US. They're used as museum pieces. And if you want to see the Soyuz in real life, you can go see the launches in Kazakhstan, in what's called the Baikonur Cosmodrome. It's a wonderful place. So we'll go to the next slide here. And so this slide is talking about, now that the space station is fully assembled, we have to talk about some vocabulary terms. So
we are unable to check you online.
So the space station is orbiting Earth, and it's flying around sort of like an airplane. It's going in one direction, and it maintains that direction all the time. And so if you're sitting on the space station and riding it in the direction of travel, what is it called? What is the direction called that faces the direction of travel? It's on the slide. Can anyone chime in? The direction that faces the direction of travel.
Forward?
Yeah, oh, I moved slides. I'm sorry about that. Let's go back. There we go. Yeah, that's forward, exactly. And so if you're facing the direction of travel, what direction is behind you? What's that called? Yeah, exactly, the aft. And if you're facing the direction of travel, what is to your right? What is that called?
Starboard.
Exactly, starboard, yeah. And if you're facing the direction of travel, what is to your left?
Port.
Port, good. Now, if you're facing the direction of travel, what is the direction that is pointed away from the Earth? Does anyone know that one? It's a little tough, but it's called zenith. And then the direction of travel, the direction that is facing towards Earth is called nadir. So these terms are important because they're used on the International Space Station to orient yourself. And when we see some videos of the space station, you'll see these words on the walls because they help the crew orient themselves when they're inside. It's okay. I'll go to the next slide. And actually, now here, I'm going to go and play a movie. So let's go to the movies, and I'm going to play a little video on the screen of the space station getting assembled. Let's see if this works. Yeah. So this is a video of the space station being assembled over 10 years. So you see the first pieces being attached in 1998 and 2000, then solar panels appear. The US lab gets attached, and the Canada arm gets attached. This arm helped assemble all the pieces on the space station after it was attached. Now you see the truss being built. This big truss holds the solar panels up so that the space station can be powered by the sun. And you'll see more solar panels appear as the space station gets bigger. There needs to be more power. More solar panels again. And then you get more solar panels. Then there gets to be a new node that's called Harmony, and that enables more modules. That's the Columbus module from Europe, and that's the Japanese module. And now there's more laboratories. And with more laboratories comes the need for more power and more solar panels. So now it's 2010, we're nearing the end of completion. And they've just added the Tranquility module with the cupola. This is the window with the person inside that was shown on the first slide. So it was near the end of the space station, but it's one of the best additions. And so what you see here is the final configuration of the space station over the course of over 10 years. So we'll go back to the slides. And that's what you see here. Okay, so we'll go now to international partnerships. And so, as I said before, this great engineering and science and partnership model was only made possible with the cooperation of all these space agencies. And this is a timeline of the assembly of the space station, and it shows the contributions from each of these space agencies. So in red are
Scott,
all the...
we cannot see the presentation.
Oh yeah, you're right. Thanks for pointing that out. Okay, now it's there. Okay. So I'll rewind. So this slide is showing the timeline of the space station being assembled from 1998 to present day. And you can see the great contributions from all 5 of the space agency partners and even international partners that are not part of the 5 space agencies that contributed. So in red, you see all the contributions from Russia, and that includes the first module called Zarya, which means dawn or sunrise. The second module, which is called Zvezda. Does anyone know what Zvezda means in Russian? So Zvezda means star. And the third module, the third component from Russia is called Pirs. It's an airlock that allows people to go outside of the space station. Then came later in 2009 and 2010, research modules called Poisk and Rasviet. And then in blue, we see all the contributions from the US, from NASA. So the first contribution in 1998 was the Unity module, and then later the Destiny Lab and the Quest airlock, And then the US made a lot of the truss and the solar arrays and a couple other modules. And then the European Space Agency added the Columbus module and contributed to the Harmony node in 2007 and 2008. The Japanese Space Agency, JAXA, contributed the Kibo module, which is shown in gray, in 2008. And Canada contributed the Canadian arm. And then certain pieces were made by international partners, one expedition in 2000 and then another one in 2011. But there's a lot of countries that were involved in the assembly of this great space station.
Logan, click capital YE.
And what you see here are the interdependencies and responsibilities of each partner. The space station is an interdependent structure, meaning one country cannot operate it all by itself. It depends on all the countries working together. Otherwise, it won't work. And so here on this slide, you see the contributions from each of the 5 space agencies. So Russia contributes propulsion. The propulsion is necessary to reboost the space station up into higher orbit, to control the attitude, to avoid debris, to eventually deorbit, and to allow resupply of the space station. Also, Russia contributes oxygen for the astronauts to breathe and removes carbon dioxide to make the air, to remove the waste product of human breathing. And then Russia has laboratory modules also. Japan contributed a laboratory module called Kibo. Does anyone here speak Japanese and can explain what Kibo means? Anyone from Japan here?
One of our tutors, Elizabeth Tasker, I wish if she was here, she'd be able to contribute, but she's not.
So Kibo means hope in Japanese. And NASA contributed gyroscopes to control the attitude, power from the solar arrays. So without NASA's contributions, the space station would have no power from the solar arrays. NASA also contributes data relay satellites to downlink the data. And in addition to Russia, it also produces oxygen and removes carbon dioxide and contains laboratory modules. Europe contributed a laboratory module called Columbus, named after the famous explorer. And Canada contributed a robotic arm called Canadarm2, and that helped build the space station. It grabs the pieces and puts them together. On the next slide, we see all the modules that were contributed by each space station. You saw all these modules fast forward in the video. But if you want to reference exactly what pieces were contributed by what space agency, you'll see those pieces here in this module. So Russia contributed some cargo modules, a service module for people to live in, small laboratories, a big laboratory, and all the propulsion that's used to control the attitude and orbit of the space station. Europe contributed a laboratory called Columbus, I mentioned that before. Japan contributed a laboratory called the Kibo, mentioned before. And Kibo is unique because it has inside laboratory and outside laboratory. So research can be done inside the module or outside. Canada has the robotic arm that contributes to the maintenance and assembly of the space station. And NASA has a lot of pieces. Most of them are related to the truss, which holds the solar panels and brings the power to the space station, electrical power. So now I'll go to the next slide, which shows all the great achievements of this space station and what makes it unique in history. So this space station is a space station that combines the efforts of many, many countries, but there are no borders in this space station. You can travel between each of the countries' modules freely. You can access all the pieces of the space station. There's no doors. It's one of the largest international partnerships in the history of science, and it united Europe, the United States, Russia, Japan, and Canada in the pursuit of these scientific objectives. It's also, in addition to this great achievement in international partnership, it's also a great achievement in engineering. It's one of the largest engineering structures that has ever been made, certainly the largest that has been in orbit. It's the length of a football field, but the components that were used to build it, all the rockets and all the ground facilities, really make this space station a lot bigger than just a football field. The solar arrays themselves are 73 meters long, and the speed of the space station is orbiting the Earth at 28,000 kilometers an hour. It's really fast. So fast that it orbits the Earth once every 90 minutes. So that's 16 times per day. It's orbiting the Earth 16 times per day. That's 16 sunrises, 16 sunsets every day for the crew on the space station. That's how fast it's going. And it's orbiting the Earth at an altitude of 400 kilometers. So this is considered a low Earth orbit. It's not that high. It's about the distance, for those living in Europe, it's about the distance from Cologne to Paris. So not that high. It takes less than a day to get there. And the volume of the space station is about 388 cubic meters. So that basically means about 6 people, sometimes more, sometimes less, can live there at any given time. So that brings us to the final slide, which is some frequently asked questions. And so at the end of this lecture, we would like you to be able to answer these frequently asked questions. So I've put the 8 questions here and 8 answers. And so number 1 is, the question is, who operates the space station? And so who wants to answer that? The answer is on the board. I haven't hidden any of the answers. So who can chime in and say who operates the space station?
So you have Russia, USA, Japan. Anybody else wants to do the other ones?
No, you go ahead and finish it off. It's
Europe,
okay.
Canada.
Perfect. You got it. So these are the partners for the space station. And number 2 is, how is the International Space Station interdependent? And that means, how do these 5 countries depend on each other to operate the space station? Can anyone answer that?
You have propulsion, power, data transfer, and life support.
Exactly. So each of these systems is controlled by different partners, and therefore they all depend on each other. And so number 3, the question is, what areas of Earth does the ISS fly over? And this is a bit of a technical term here, but can someone answer this?
No.
So it flies over 90% of the area of the Earth where people live, which includes everything from Russia down to Argentina. And so that is most everything that can be accessed with this inclination, which is 51.6 degrees. I'll talk in detail about what that means in the third lecture on operations. But basically, the International Space Station flies over 90% of where people live on Earth. And it can be seen without a telescope from most of these places. Number 4, can crew arrive and depart on different spacecraft? We didn't talk about that, but the answer is no, not usually. Usually, if a crew arrives on the Soyuz, they leave on the Soyuz. Or if they arrive on the SpaceX, they leave on the SpaceX. They don't usually switch. Number 5 is, do NASA and Roscosmos always need crew aboard the space station? And that answer is yes. The reason why is because NASA and Russia control different parts of the space station, which are interdependent, and the Russians cannot do the things that the Americans can do, and the Americans cannot do the things that the Russians can do. So there needs to always be at least one person from each country on the space station to run the systems. And number 6 is, how is attitude controlled? Attitude means the orientation of the space station in space, to make sure that it's going in the right direction. How is that controlled? Does anyone want to answer number 6?
So utilizing propulsion.
Exactly. So does anyone remember which country controls the propulsion of the space station? It's one of the countries in number 1.
Russia.
Exactly, Russia. Number 7, how long will the International Space Station be in operation? This we did not talk about, but it's in the 5th lecture. We'll talk a lot about that in the 5th lecture, but basically the International Space Station is planned for operation until at least 2030, but the condition of the space station is reevaluated every few years. And so the current certification goes until 2030, and that's how long these 5 international partners have agreed to continue operating it.
Scott,
and we'll talk about what happens.
Sorry,
Yeah.
I was just going to interject here only because we know that the space station is potentially going to be up till that time, but of course, new space stations or commercial space stations are being built. And the reason why I bring that up is from your lecture, we've also got Tara Rutley here, who is obviously the chief scientist for Orbital Reef. So it'd be great for you two to have just a quick conversation on what that means. So Tara, if you're able to join us, it'd be great.
Yeah, can you guys hear me? Okay.
Yeah, we can. If you want to come forward, and we'll get you and Scott together.
Hey, Scott. I'm going to attempt to walk forward.
Please, yes, you're welcome to speak about this topic. Please.
Super presentation, super models. Everything's beautiful. It's just as for everyone in the audience and for Scott, I worked at NASA Johnson Space Center for about 20 years on the International Space Station. We managed the science. So I was associate chief scientist. So this has been a fun lecture. I think the whole course will be really cool. But I'm not there anymore. I am not at NASA anymore. I left NASA last year to go to work for Blue Origin, which is a private space organization. And one of the things we're doing there is building a commercial space station that we plan to provide for NASA to replace the International Space Station once that is decommissioned at the end of 2030 or whenever NASA decides that to be the case. So my job there is to basically get the science facilities up and running, or at least design them, get them managed, figure out which ones we're going to need to support NASA's needs, but also not just NASA, but for anyone else who wants to do science on our space station as well. So it'll be a little bit different than the International Space Station. It'll be a little bit bigger and more accessible to public and private individuals who'd like to participate. But just want to say, great lecture. If there are any questions on that, you're welcome to ask.
Thanks. That's very kind. Okay, and just to give a little preview for the fifth lecture in this series on the International Space Station, we're going to talk about in that lecture what happens after 2030 with the International Space Station, with the possibility for commercialization. Companies like Blue Origin, Axiom is another player who's already operating on the space station. So we'll talk about those things in the fifth lecture on the future of the space station. And then number 8 here, just to finalize this slide, how will ISS be deorbited? If it is deorbited, and that is the answer to that question is safe re-entry into remote ocean by propulsion, which again is discussed in the 5th lecture in this series. Okay, so that is the final slide in this first day of the International Space Station lecture series. And this is the first slide of the next presentation, which we won't go into, but what I want to do now as the final introduction is give you a 360 tour of the space station, led by ESA astronaut Thomas Pesquet. He made this video, and I'm going to play it, and we're going to all be transported into the 360 room. Camilo, is it okay for you if I transport people to
do you want me to
360
transport
room?
them, or you want me to transport them, or you have it there?
I can do it. I just want to ask if that's okay with you.
Yeah, absolutely. Let's
am I
do
allowed
that.
to do that?
Yeah, they will love it.
Okay.
Yeah, absolutely.
Okay, everyone, hold on to your hats. We're gonna fly to a different location, and in that location, we're gonna play a 360 video. Okay, is everyone ready?
We are.
We're ready.
Here we go. Okay, everyone.
Hi.
So
We're
all of
gonna
you need to
have-
move. Just start moving around. Yeah, start wandering around.
We're gonna be on the space station in 3 seconds. Ready? And we're now going into node 1. Now we're in the US laboratory Destiny, floating slowly.
Oh, we should have VR.
And now we're in node 2,
Yes.
the Harmony module. And if you look around you, those are the crew compartments where people sleep. On the port side is Kibo, the Japanese module. And on the starboard side here, in the direction of the camera, is Columbus. And I'm going to pause the video here. This is the European laboratory where the astronaut, Thomas Pesquet, the person taking the video, this is where he worked during his mission. His mission was called Alpha. That's the patch on his shirt. And surrounding you, you can see all the research experiments that were conducted by the European partner countries during Thomas Pesquet's mission. And so I want to end the video here as just a kind of a cliffhanger, so to speak, for the next lecture, which will talk about these science experiments in these racks around you on the space station. So that's it on my side. I guess that's 52 minutes, a little bit longer. But now I leave it to Camilo and Wasim to tell us what's next. Thanks, everyone.
Scott, thank you very much. This was amazing. This was an amazing lecture. I think, of course, you deserve like all our respect and clapping our hands for such a beautiful presentation. Guys, if you have any questions, please feel free to unmute yourself and make all the questions to Scott. Isha, you said you had a question earlier. I don't know if you would like to make it now.
Before that, Scott, I just want to say what a fantastic lecture. Thank you so much. This was absolutely incredible. By the way, I had no expectation of this part. So thank you so much for putting this together. I do have a question from a live audience outside the VR. This is more of a comment from David in terms of the commercialization of space. I know we're going to be going into details of that. But Scott, for those people who look at space and look at space station, just to summarize, why do you feel it's important that majority of populations understand space and get involved in what's happening out there?
That's a great question. So the space station is important because it's a laboratory, unique in the world, so to speak. It's not on the world, it's orbiting the world, but it's unique in the world because it allows for research to be done in microgravity, which is a unique environment that allows us to understand how humans, how physics, aspects of biology work off of the Earth. And by understanding how things work off of the Earth, we can improve things on the Earth. For example, osteoporosis is a disease that affects many elderly people worldwide. But osteoporosis also affects astronauts because in microgravity, bones are demineralized, similar to what happens to old people. And so if we can understand how to keep the astronauts healthy in space, we can solve a medical problem for millions of elderly people around the world. This is one example of hundreds of science applications that are conducted in space that have the benefit for Earth.
Amazing. And Tara, this one's actually for you. When we talk about commercialization and new space stations like the ones you're building and people like Axiom, how do you feel that's going to make it more accessible? And also, how do you think that will contribute to bringing more industries into this space?
Well, as Scott mentioned, the last 20 years of the International Space Station has been mostly government entity participations by major partners. NASA's gotten really good, and our partners also have gotten really good at opening up the space station to what we call commercial space, which is managed by, I don't know if many of you know that the International Space Station components that are owned by the United States is also called a national lab. So that means that many of the assets on the space station can also be used for private industry and business. And anybody who's not NASA, as long as you follow some of the guidelines internationally and participate under certain conditions, I should say. So some of the constraints of the current International Space Station has been that it's not open to everybody globally. It's been mostly government astronauts, mostly government agencies with a little bit of business participation from around the world, but very selective. Now, these new commercial space stations won't have so many governmental restrictions and therefore are open access to more individuals like you and I, and even more countries who want to participate who didn't get a chance to do that with the International Space Station. So it's going to take a little bit of time for these commercial space stations to come on board, but that's what we do. We're spending a lot of time right now talking to folks around the world like you and businesses and other government agencies to see who wants to participate and in what way do they want to participate. Do you want to do research? Do you want to have educational activities? Do you want to simply visit? There are lots of opportunities for a lot of folks. And so it's the fun part about my job is getting to talk about that and getting to talk with folks from around the world who have the best minds for science, in my case.
Amazing. And Scott, the DLR or the German Space Authority, they've got a robot in space called Simon, if I'm correct. And what do you see in the future in terms of AI and robotics playing a role? And the reason why I asked that question, for all of you people who are asking, if I do AI, if I do robotics, how that pans out into careers, not just terrestrially, but also outer space. So, Scott, if you could tell us what you envision the role of AI and robotics being on the next space stations.
Okay, that's a great question, and I'll answer it because in terms of I'll answer it broadly, because the German Aerospace Center DLR is just one of many contributors to robotics and artificial intelligence. The Simon robot is one of many. The NASA, for example, has AstroBee, which is floating around. We'll actually talk about AstroBee and Simon in the second lecture. But for now, these robotics have been inside the space station together with the crew, and they've done things like search for things around the space station. As you can see around you, it's a mess, and so finding things can be helpful with this type of AI automation. Also, these robotic partners can be used as companions, sort of like Amazon Alexa in your home, or one of those other like Siri. Those robots can operate in that way. That's Simon's functionality. And this might be necessary for longer duration missions where there's more isolation. That was the theory behind that was the rationale behind the Simon robot. But that's just the inside of the space station. Robotics is also applied to the outside of the space station. The Canadarm is a perfect example. That great robot was built in Canada, launched to space, and then that robot built the space station. So now there's more than one robot on the outside of the space station. The Japanese module has a robot which is outside on its experimental platform, and it coordinates the experiments on its outside platform. And the European Space Agency now also has a robot attached to one of the Russian modules. And so these robots serve right now to maintain the outside of the space station, replace parts, help crew members move things around. And these robots are controlled from the inside of the space station in the US lab, which Thomas Pesquet took us through on his way here, and inside the cupola. And we'll see in the third lecture in this series, in the operations lecture, we'll see how to operate the robotics.
Wow, what a great answer. For all of you who've been watching these lectures and hopefully will be joining for the ones we're going to be doing going forward, our goal really here is to really help understand that we're going through this massive environment of change. And these subject areas today that we are looking at for our kids or the current workforce is going to be an interdisciplinary approach into everything we do. So the lectures and the work that we're trying to get across is chemistry, maths, entertainment, music. It all links. So my final question, and I'll leave this one for you, Tara, and then Scott for you to finish, just because it was such a brilliant one. Tara, for those who are thinking careers in the future, how space links in, could you give us any insight into why these subjects matter? And then Scott, I'll leave it to you to end the session.
Oh, well, the reason these subjects matter is because not only are you going to have a future, we're going to have a future as humans in low Earth orbit, we're also going back to the moon. So you know, from a scientist perspective, those are all resources for me to be able to have new discoveries and do new experiments. And so the discovery for new cases for medical treatment or new materials or new processes that we can improve lives on Earth is really, really important to me. And whether you do it in low Earth orbit, like on a space station, or whether you do it on the moon, there are advantages and challenges to each. And so for anyone who's looking towards a career in the space industry, I'd say, you know, science is one, but if you think about also going back to the moon, and that more and more people will likely be going back to the moon as the moon population grows, you know, just about any career that you can think about on Earth, you think about how it might apply to being on the moon too, because anywhere there's humans, humans will need the same safety, same services, same entertainment, same, you know, health management as on anywhere as you on another planet or the moon or in low Earth orbit as you would here on Earth. So think about the things that you're interested in now, and think about how you might use those talents, those skills, those interests, either in low Earth orbit or the moon, and it's all applicable.
Perfect. And Scott, we're going to let you end it with an answer to the same question. And again, personal thank you. I did not expect this part of it, by the way. So you completely stole it away from me as well. And we've been doing this for a year. So well done.
Thank you. I'm sorry. Maybe you have to repeat the question.
The question was, how, for those people watching, how space is relevant to careers in the future, whether you're going to go into the industry or not, but by being involved in astrobiology, by being involved in the subjects we're talking about, you know, how can that help create a pathway for a future career?
Okay, I'm going to answer this question differently from a United Nations perspective. The United Nations has Sustainable Development Goals, which are, there's 17 of them. And a great number of these Sustainable Development Goals can be monitored and improved through space. For example, one of the Sustainable Development Goals is focused on climate action. Climate is a big topic, and there are a large number, let's say 100 or so variables that are used to measure the climate on Earth. About 69 of these 100 or so variables can only be measured from space. And so that's why space is important from a climate change perspective and from a UN Sustainable Development Goal perspective. Space just gives us a bird's eye view, and it's a region that inspires people. And I think that's a different way of answering the question, I guess.
No, that's perfect. Scott, thank you so much. Tara, thank you for your contribution. And everybody who is watching, we've got the next lecture starting straight away. So thank you so much for everybody who attended. So everybody's here. If you can stay in here, if you're able to stand the next lecture.
We will go back to the dome, guys.
Perfect.
So don't worry. Just stay here. We are going there now. Welcome, everyone.
So those of you who are watching will be going on the next stream, which will be on the same link, so you'll be able to watch them. So those who are engaged, great. And we're just going to change over.